Now that we know how to define what a rate is and determine rates from experimental data, we want to talk about what are called rate laws. A rate law is an equation that lets you determine the rate of a reaction as a function of reactant concentrations. So when I say rate of a reaction, we're talking about overall rate, right? The idea of calculating what the overall rate is, that single number that describes the reaction. So this is going to let us calculate that. And so one of the ideas about a rate law is it takes the concentrations of reactants and it tells you how fast the reaction is going to go. So that's beneficial. You can predict the rate for a given setup. More frequently, it's used kind of in the other way, that you have a target rate. I want this reaction to go for at a certain speed. What should I make my reactant concentrations, right? I want them to be so high because I want the reaction to happen at a certain pace. Or you may want to avoid a reaction occurring, right? The reaction's really slow, you're going to be producing something toxic, and it's good as long as you keep your concentrations low. Something like that. So you want to have that idea, something along those lines that gives you some sort of target. You want to keep your rate low, so what do you need your concentration to be? But knowing a rate law, we say that that completely determines the reaction kinetics. You have a complete understanding of reaction kinetics. And importantly, if you know the equation for the rate law for a given reaction, you can make any prediction about how fast the reaction will go for a given set of conditions. What are your concentrations? So what a rate law looks like is this. Rate is equal to K times the concentration of A and in brackets up to the X power, concentration of B to the Y power. It's important to note this is again for a generic reaction. So capital A is the formula of one of your reactants, B is your other reactant. However many reactants you had, they would just show up here. So if you had 3 reactants, all 3 of them would show up in the expression. One of the things to note, rate is directly related to reactant concentration. So we've seen this before, that as you kind of get a slowing down of the reaction rate as your reactant concentration decreases, and that's a direct thing that comes from the rate law. As you have more reactants, your rate is faster. When you have less reactants, your rate is slower. So that's one thing we can take away from this. That's always true, that the rate law is reflecting. More reactants, higher concentrations of reactants specifically, means faster rate. So what are the different parts of this here? Well, first you can see we have this lowercase k. Rate, this is called the rate constant. So this is just a number that is unique for your reaction at each temperature. So you do need to know the temperature that you have, and you need to know what reaction you're dealing with, and as the temperature changes, K will change. High values of K mean higher rates. So fast reactions have large values for K, which makes sense. It's just a number here. Maybe take your concentration, multiply it by a big number K, you'll get a big rate out the other side. So then the concentration, the A and B in brackets are just the concentrations of reactants, and the X and the Y are exponents that are the orders of reactants. So these are the powers that the concentrations are raised to in this equation. You will note I've used X and Y, not little a or little b. That is because the order of a reactant is distinct from the reaction coefficients. Reaction coefficients have nothing to do with this here. For now, the orders that we see here, they can be fractions or decimals. Generally, most of the time, they're going to be whole numbers, and they're going to be low whole numbers. The most common orders that we will see are 0, 1, or 2. Those are really all that you really see. For the most part, they are going to be whole numbers for most reactions. So when we are given a rate law, we want to be able to kind of parse out of it what we're looking at. So rate is equal to K, then I have square bracket C, square bracket D with that 2 there. So what this would tell me is that the order with respect to C is going to be 1. There is an implied 1 here. That's the exponent on the C term. We don't write the exponent if it's 1. So if there's no number written there, that implies that it is first power. This is a first order. So C is first order, is what we would say. The order with respect to T, C is 1, C is first order. We have this different language that all means the same thing. With D, we have the 2 right there. The 2 is shown, it's second order. So D is second order. So each reactant has an order and there is an overall order. And you just add up the orders of all your reactants. And so you'll note I haven't even written what the chemical reaction, the equation is. You don't need it because those equations don't matter. The coefficients don't matter. The orders are independent of those. You just need to know what the reactants are. You're reacting C and D, and this is how you would describe the rate. And so the overall order of the reaction will be just the sum of all of the orders of all of your reactants. If you have 3 reactants, you'd add all 3 of them up. So what is the purpose of the order? The purpose of the order is to show the effect of changing that concentration on the overall rate. So C is first order here. So because it is first order, if you double the concentration of C, the rate will also double. We know that if you increase the concentration of your reactants, the reaction goes faster. The rate always increases. And so the order basically takes that increase and has it affect determines how it affects the order. Because if you just times 2 right here, it's going to be times 2 over here. Because D is second order, if you double the concentration of D, it would quadruple the rate. So basically what happens is because there is this 2 right here, what happens is you do the times 2, you could imagine, within that power, within the 2 power, where that's your order. And so you would get 4 overall times that, right? The 2 goes on to there. And so the rate would go up by 4. So whatever the order is, however you affect the concentration, you double it, triple it, quadruple it, you raise it to that power, right? So you're always going to raise it to the power. That's the effect it's going to have.
One important consideration when we're looking at rate laws is what the units are on K. So we know that rate is going to have units of molar per time. We're going to say seconds, but this would apply to any sort of time. Concentration of C, because there's the brackets, is molar. Concentration of D, because there's brackets, is also going to be molarity. And so if we look here, what we can do is we can kind of figure out what the units of K need to be by setting it up like an algebraic expression. I'm only going to look at the units here. So I know my units on the left-hand side need to be molar per second, whatever the units on K are. C has concentration of molarity. D has concentration of molarity, but that's raised to the second power. So if I want to isolate out K, I'm going to take those numbers and divide them out. So molar seconds, molar squared is equal to K. So those are going to cancel. And so what that tells me is that the units on K for this reaction is 1 divided by seconds times molar squared. And so the units on K are always going to look something like this. You're always going to have these values in the denominator. Important to note, this is also oftentimes written in the denominator as s to the -1 times m to the -2, where those negative exponents just mean they're in the denominator of a fraction. It's very frequent that you see them written like this, though, because it's just a little bit cleaner. And honestly, it's like easier just to type out in like a word processing format. So that's really common on Sapling. It's common in the book, just to use that representation, just to kind of clean everything up, make it a little bit easier to deal with. And so you can see this comes from this. One of the things you can see is that the units were affected by how many molarities we put down there, which was affected by this side of the rate equation. So units on a rate constant actually depend on the order of the rate law. So our general expression is that the units are going to be 1 divided by molarity raised to the power of the overall order minus 1 times seconds. So if you note for this reaction, the overall order is 1 plus 2 gives me 3. So if we look at, say, this equation, if we want to come up with this, it'd be 1 molarity to the 3 minus 1 times seconds, which is 1 over m squared times seconds, which is what we got. Again, wherever I'm writing seconds, that can be any unit of time. You can have days, years, millennia, if you have slow chemistry. The unit on the molarity is what's going to change. The unit on the molarity affects how this, is based on the order, and then kind of cleans it up. It doesn't really change the meaning of the rate constant. It's still going to be the case that big rate constants imply faster reactions. It's more of just a bookkeeping concern to make sure that your units work out, because rate always needs to be concentration per time, and your input concentrations always need to be concentration.
This dependence on the units of K on the order of the reaction are going to be really important. One, just because it's something we really want to be mindful of when we're solving problems, when we're obtaining rate constants, that unit can change. But it's also something that really helps us in a lot of ways when we are being given the rate constant. A lot of times people who are, like, if you want to be super sharp in the know, you don't say what the order of a reaction is. You just say what the units of the rate constant are. And you can always figure out the order because it's cooked into there. So that's kind of a sharp, it's like, hey, yeah, I don't need to tell you what the order is. I'll just tell you the units of the rate constant. It is, of course, being obtuse, but it still is something that happens quite frequently. And I'm going to tell you right now, I'm going to do it to you. So you can use the units on K to figure out order. All right, let's look at an example now of analyzing rate laws. Consider the following reaction equation and the associated rate law. I have A plus 2B becomes C, and the rate is equal to K, and then square brackets A squared. I got a couple questions I want to know. What is the order for each reactant? What are the units of the rate constant? How would the rate increase if the concentration of A doubled? How would the rate increase if the concentration of B doubled?
All right, so if I want the first question, what is the order for each reactant? So if I want the order, what I'm looking to is going to be the exponents in the rate law. I don't care about this, exponents in the rate law. So one of the things we can see, there's the 2 power, that's second power right there on the A. So I know right away that A is second order. So my other reactant is B. So B also has to have an order. So that's where the chemical reaction just tells you what the reactants are. You need one for A and you need an order for B. If I look at the rate law, I can see that B doesn't show up. B is not contained in that rate law. So the question is, what would the order be? Well, the order in this case is going to be 0th order. Because if we have the concentration of B raised to the 0th power, that is equal to 1. Everything raised to the 0th power is 1. So basically, you don't write out B to the 0th. You could say that technically the rate is equal to K concentration A to the second, concentration B to the 0. But that just all goes to 1, and you're left with just the K concentration A to the second. So when you have a reactant that does not show up in the rate law, that is 0th order. What are the units of the rate constant? So units of the rate constant, we could go through the process of like plugging in units for everything and trying to get the units on K sorted out. But what we can also do is we can just use our overall expression. We know that the units, it's going to be 1 divided by m to the overall order minus 1 times s. So the overall order is 2 plus 0. So I put in the 2 minus 1, and I get 1 over m times s. And we can also write that as m to the -1 power times s to the -1 power. So either of those would be accurate representations. We can also tell if we were only given that unit, we know right away that overall this reaction is second order. You'll note we can't parse out what the orders of the independent, the different reactants are, but we do know that overall it is a second order reaction. All right, so we're going to use this information. How would the rate increase if A is doubled? So this question of how would the rate increase if you have some sort of change in concentration is the purpose of order. So the order tells you that the concentration of A is raised to the second power in the rate law. So what you do is you basically take this value, so you're saying you're doubling it, so you do times 2, and you raise that to the order. So you times 2 to the second power. And so that tells you that it would be times 4. So the order is always as an exponent. So basically, if you times it by 2 here, that times 2 would get squared, and the rate would increase by 4. So because A is second order, it has a changing its concentration has a bigger effect on the overall rate. You get big bang for your rate, you get double bang for your buck. You get the times 2, giving you a times 4 increase in rate. So if you want to, one of the things this tells you, if you want to make this reaction go faster, because A is second order, increase its concentration and you will see some dividends. You will see a nice increase in the overall rate of the reaction, which is what you want to do. All right, so then in this case, we're going to double B, concentration B. So I'm going to do times 2. And then again, I want to take out the order. Well, the order in this case is 0th. So I'm going to do times 2 to the 0th order, and that is equal to times 1. And so how would the rate increase if B doubled? It wouldn't. You would take the rate and multiply it by a factor of 1, which is unchanged. So what this tells us is that things that are 0th order do not affect the rate. This is consistent with our rate law expression. The concentration of B is not in here. The rate of the equation is not affected by the concentration of B. So as you increase the order, you do see larger effects on the rate by increasing the concentration. As you decrease the order, you can eventually get no effect on the rate based on concentration. So because B is 0th order, if you double its concentration, the rate just doesn't change. The rate does not depend on the concentration of B, so increasing or decreasing the concentration of B will not affect the rate of your reaction. Participation 128, question 2. Consider the following rate law for a generic reaction. Rate equals K, concentration A, concentration D squared. What is the order of A? How will the rate change if the concentration of D is tripled? And what are the units on K? So basically, I got a rate law and then just a generic rate law, and I want to know those 3 questions, answers to those 3 questions. The second question on participation 128, due Friday, January 28th at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Consider the following rate law for a generic reaction. Rate is equal to K times concentration A, concentration D squared. What is the order of A? How will the rate change if the concentration of D is tripled? And what are the units on K? So I want all 3 of those questions answered.
So now that we're familiar with what rate laws look like and kind of the different parts of them, the different features of them, we want to return to their importance. Rate laws fully describe the kinetics of reaction, right? You can predict the rate for any reaction conditions at whatever temperature you're looking at. And that lets you design reactions. How many of all the different reactants are you going to put in to obtain your desired rate? You want to control how fast your chemical reactions are occurring. So in order to do that, for any given reaction, you need the rate constant and you need an order for each reactant. Okay, so each reactant needs an order and you need a rate constant. So you need that for everything. It is impossible to get a rate law from looking at a chemical equation. You'll note I haven't put up a ton of chemical equations because they don't matter. The only thing the chemical equation tells you is what all the reactants are, and then that tells you what things you need orders for. But the coefficients can oftentimes be distracting. We want to use them, but they're not meaningful. We'll eventually see at like the end of this chapter where they can come in and where orders come from. But for now, we have to get these things from experiment. So rate law implies it's a summary of experiment. So we need to analyze experiments in order to determine how to come up with a rate law, which we'll talk about here in the next video.
Pretty back heavy on those participation questions. I got one more video. I'm guessing we'll find another one there. See ya.